Greetings. Welcome to another Insight Project video. Welcome. So in this video, I'm going back to obviously spinning things. And what I want to do is I want to run this motor off of a supercapacitor and at the same time see what I can do in terms of charging another supercapacitor at the same time, not with any conventional sort of pickup coil, but just with what's going on from this coil. So I know I've gone over this repeatedly, but if people are joining in for the first time, I'll just kind of talk through the circuit real quick. So you have this coil, you have these magnets on a rotor, and they're arranged north-south, north-south. You could also, with changing the circuit and the code just a little bit, have them all north-facing. That would be monopole, and this is called bipolar commutation. Over here you have what's called a Hall effect sensor. The output of the Hall effect sensor differs depending on whether it's seeing a north or a south magnet going past, and the Hall effect goes to the analog digital converter pin on the Arduino, and depending on the number that comes out, you either pulse this thing to pulse one way for a north magnet and then pulse the opposite way for a south magnet. So that makes it spin. Then you have over here 4 diodes that are arranged as a full wave bridge rectifier, and those yellow lines are going to the 2 ends of your coil. And so there's a voltage that comes out of there, and it's of course now a DC voltage because it's been rectified by the 4 diodes. So why is there a voltage showing up across this coil? And there are 2 reasons. The first reason is that it's a pulse motor, and so it gets a pulse, shoots this, and then it shuts off, and then it comes around again, pulse, shoots this, then shuts off. Now when it's shut off, all you have is a coil sitting past magnets that are spinning past. So if I just did that by hand and put a cap there and a voltmeter, you'd see a voltage showing up. So that's part of it. And then a second reason is that you have a pulse, and that generates a magnetic field that goes up, and it's a brief pulse, and then the magnetic field goes back down and collapses again. And that's where you get what is termed the flyback. When it collapses, there's a voltage that flies back, and that gets rectified as well. So there are actually 2 sources of how voltage and current can be coming out of this. And I've done lots of videos just on how to hook the Hall effect to the Arduino and how to build this circuit and so on and so forth. So if people want to dive in and replicate this, there's all the videos for how to build it. So now, why am I going to run it off of a supercap? This is really thin wire, and when you have this thing at like 5 volts and you put it across an amp meter, you'll have this thing spinning along, and you can find places here with the correct angle of the Hall effect and your coil where you're drawing about, it's like, oh, I think that's 1 milliamp. Maybe it's 2, well, maybe it's a half milliamp. But it's like 1 milliamp. Now, granted, the thing is very low torque, but it's incredibly efficient. It's like 1 milliamp. So just to give an idea, this rechargeable Duracell that I picked up, it's, I don't know if I can show it. It might show up on the camera, but it's 2,500 milliamp hours. So drawing 1 milliamp, 2,500 milliamp hours, 2,500 hours later, you have your answer. If you're going like battery to battery, which would be a little over 3 months. Now, granted, when it's loaded, maybe you're going to be drawing, 5 milliamps or something like that. But it's very, very low amperage. And so first thing, I went to these Tenergy rechargeables, and I went for the lowest capacity ones I could find, which is like 270 milliamp hours. So now, let's say you're drawing 10 milliamps. You're still at 27 hours to say what's happened if you tried to run it off here and then go to another battery. So now you have these supercapacitors, and I've written down that it's they're 5.5 volts and 2.2 farad. I only have 3 of them. I wish I had 4, because then I could run it at 10 or 11 volts. But here we'll have to just go with 2 of them and run it at 5 volts. But let's do a back of the napkin calculation, and if I get this wrong, someone can correct me. So the charge in a capacitor is equal to the capacitance times the voltage. So if we charge it to 5 volts, we have 5 times 2.2 would be, you have 11 coulombs of charge. Now, what is an amp? An amp is when you have a flow of charge of 1 coulomb per second. So we have 11 coulombs of charge to flow, and so we have 11 amp seconds. Therefore, we have 11,000 milliamp seconds. There are 3,600 seconds in an hour. So 3,600 times 3 would be 10,800 seconds in 3 hours. So you have just over 3 milliamp hours if we wanted to convert it to how these are. This one's 2,500, this is 270, this is like 3.1 or 3.2 milliamp hours. So that's going to be 100 times faster than this. So in other words, you should be able to get your answer in 5 or 10 minutes. Just run it off of here and see what's working better, what's working worse. Now, there's going to be a lot of things that are going to be different than going battery to battery, which, you know, when this thing starts out empty, I mean, I'm thinking it's going to view that almost just like a dead short. And then as it begins to charge up the capacitor, then it should draw less and less current. But initially it should draw a lot. Whereas even when a battery's dead, it's not looking so much like a short like an empty cap is. But really it's just, can we get useful information out of what sort of arrangements here work better and which ones work worse? And that's what I'll look at. And as I showed in the previous video, and I'll try and show a little bit of this time as well, despite this being a really simple motor, you're just pulsing it or whatever, the behavior just changes wildly depending on the angle between the sensor and your coil, so when it's being triggered. So there are places where, like, you're drawing 20 milliamps. There's places where it's like, I think that's a milliamp. It might be a little less, talking about it like 3 volts. And within that area where it's like 1 milliamp, there's places where you get, like 3 volts out of here. There's places where you get 30, and then there's places where you put it up to where it's drawing like 10 milliamps, but I was at 3 volts and I kind of stopped it when it was at like putting out 160 volts. It would have, I think it would have just kept going well past 200. So the question, also becomes, maybe you want it there where you're drawing 5 times as much current, but the voltage is 10 times as high. Maybe that's where you want it. Or maybe you want it, where you're drawing a little current, but it's getting like 30 volts out. Or maybe when it's drawing a little current, there's like some spot where it's like, 10 volts out. That would be really odd and surprising, but this thing always surprises me. I mean, you can't have it like if you're running it at 5 volts where there's, if there's like 6 volts coming out of there, with apologies to Yogi Berra and his restaurant review, where he says, no one goes there anymore, it's too crowded. So it's sort of like, if you get 5.5 volts out of here and you're at like 5 volts, it's too crowded. There's not enough potential difference for it to get into here. So I think, you're going to want this voltage as high as you can with as little amp draw, and then maybe you want to sacrifice and have more amp draw just to keep shooting the voltage up. So that's the first thing. And then I'll probably try and do it like twice each time. So even if these things take 15 minutes each, it's probably gonna take a little while. And then I don't think I'll get to it on this video, but this will be the next spinning things video. With a pulse motor like this, it's spinning at a specific speed, and it's on for however long the magnet's passed in front of the Hall effect. So the faster it spins, the briefer the pulse. For reasons I'm not going to go into now, the briefer the pulse, the more efficient the flyback. And so you can actually hard code that, you know, maybe the thing's there for like 4 milliseconds. You can hard code it and say only pulse for 1 millisecond. Now the problem, I did a video on this. The problem you run into there is that the thing just doesn't want to start. And then once it gets spinning, it'll speed up, but it's like there's problems with that. But one thing you could do is like have it pulse 5 times, each one a millisecond, instead of like a single 10 millisecond pulse, which might help here, but I got no idea, because the way this coil collapses, I think, is also very dependent on the environment it's seeing with the magnet spinning past. So I have no idea. I'm not pessimistic about that. I'm not optimistic about it. It might help. It might make things worse. So that's sort of the last thing on that. And then I really got to start building the next generation rotor. But I mean, I want to figure out where do things go before I start doing all that. Okay, so give me a little while to get this set up. So we'll short this one out. This one I'll run in parallel first, and then we'll switch over to running it off of this and charging this empty one. It's so stupid. I mean, I'll put some music on when I'm working, but if I like have the music on, they'll do like a copyright infringement. If I could be king, if only for a day, baby, if I could change the world. Sorry. Let's see if they ban the video. You're censored. Who does not approve? Okay, brief intermission here. I fried 2 of the channels. I fried one on each of the SSRs. And remember in the last video, I was like, I'm running it at 3 volts so that we don't fry anything. And I was thinking, how in the heck did I do that? And then you recall, while the thing was just sitting there like nearby, I had the other thing I'm working on where I'm like happily zapping copper with 5,000 volts, copper and balsa wood with 5,000 volt sparks. And so it's like, maybe I shouldn't have left this circuit near there. So I finally got it. Now all the channels are working again. So now I'll set it up and we'll go from there. I would be the sunlight in your universe. You would think my love was really something. Not Eric. Alright, well, it's spinning, yay. And I'm now officially pissed off. So here we're like over 5 volts. It still can't get a milliamp reading on there, and that would go down to 10 milliamps. So it's drawing less than 10 milliamps. If I put it on here, now it's trying to say 35 milliamps. This one says the same. It's under 10 milliamps per the thing. When I per the power supply, when I was running before, we'd be at like 2 milliamps. What the heck is different? Is it something with the circuit, or did these things somehow, I was using them for something else, did these things get fried? It's a long shot, but maybe that's it. I've got an unopened 30 milliamp one here. I'm going to put that one on. I honestly, I don't get it. I mean, under 10 milliamps, 30 milliamps. Previous video, we would have been under 5 milliamps on this meter. I may try and put a digital one on too. This is annoying. All right, so I put a brand new one there, and now it's looking like it was before. We're at 4 milliamps, which would jibe with what's being seen there. I don't know how I fried both of those. They're worthless now. Oops. Okay, well, I finally got everything running, and yeah, you can't. I was doing stuff with the batteries. I pinned those through a short, the other 2 meters, and now they're worthless. I didn't understand they're that sensitive. But, you know, now we're seeing we're like drawing an amp at 5 volts, 1 milliamp. It's spinning along. There's 38 volts out of there. And I know I've shown this all before, but, or, you know, I mean, that's the amp draw. It's actually like 2 if I center it. But if we bring it over here, if anything, it's lower. I don't have the camera focused right. It's like 2 milliamps. But now, you know, we're getting that voltage out across just a random cap across the bridge rectifier. So the next thing to do is to replace that cap with that cap and then run it off of this cap until this thing stops running and see what voltage ends up there. And that should give you a pretty good idea of where you want to put this thing in relation to there. So I'm going to have to like put a little bit of glue, you know, not like real permanent glue, but like some Elmer's glue to make sure that the sensor's in the right place and whatnot. So, I mean, I guess I'm saying, you know, now we got 111 volts and climbing, and it's a tiny bit more milliamps. So, yeah, there were some hiccups here, and I apologize. This has been going on a long time. So, if there hadn't been problems, I mean, I'd just go. But this is getting long, so I really apologize. I'm going to break it up into 2 parts. The second part, I'll actually give the data. And now, you know, I can run one of these tests, just, you know, taking it off of there, running it off of there, and I should get an answer in 10 minutes. And then, you know, move it over and find out where's the best spot for this particular setup. And again, this stuff starts out so simple. Maybe it's different for a monopole motor. I mean, this is just my setup, and I'm just trying to engineer for it and whatnot. But again, I apologize that it should that I'm going to have to, you know, I'm going to have to gather data. Each one's going to take like 15 minutes, and I'll just run it until it runs down. You know, the rotor stops and see what's there, and that'll be, you know, like 0.5 volts and see what's there. And figure out, you know, where the heck do you actually want this with this kind of particular setup. And then, you know, you know, I don't want to just like talk about stuff without doing the next thing though. I mean, even before I build like a more complicated rotor, put a second coil in. Now what happens then? Your inductance doubles, your resistance doubles. So seeing as your inductance doubles and your resistance doubles, like each one of these will pull with half the strength, but you'll have 2 of them, so they should pull with about the same strength, except for you'll use half the amps. That's as clear as I can figure it out. I mean, I think that's why, you know, there's like the Joseph Newman, you know, 2-ton machine of wire, big Eureka, and John Bedini's Ferris wheel, and who was that other guy that built some enormous John Bedini schoolgirl circuit with like a bearing that they used to launch planes off aircraft carriers or something, and like the batteries got stolen in the middle of the presentation. You know, I could be wrong about all that, but when you put 2 coils in series, the inductance doubles and the resistance halves, and the inductance is driving this. So again, sorry, but I don't want to make these like 2-hour videos. So in the next video, we'll do this, and we'll see what we saw. And I'll definitely try and get this out, like, before a week or two, hopefully like in a day or two. Although it'll probably take a day or two to just do the experiments and put them in a spreadsheet. And then know where these are, and then start, adding another coil, and then start improving the rotor. Put another part of the rotor down there. Baby, if I could change the world. Tyson Fury's got nothing on me. All right. Take care, y'all. Bye-bye.